Good morning, afternoon, or evening, or whatever it is where you are. This is a short introductory lesson on waves, and it will include no more math beyond simple algebra. So without further ado, let's get started. What are waves? A wave is a disturbance in a medium. Here are waves traveling through a pond. The water is moving up and down, but only the wave is moving across the pond. The wave is moving across the pond, the water itself is moving up and down. And at one point, light and other electromagnetic waves, which we're not going to talk about right now, do not require a medium. Transverse and longitudinal waves. The water waves on the last slide were transverse. The wave moves perpendicular to the medium, like in the slinky at the bottom. But that doesn't have to be the case. In the slinky at the top, the waves are longitudinal. They compress and expand, and the wave moves in a direction parallel to the medium. Here are some examples of both: transverse waves and longitudinal waves. Electromagnetic waves are transverse. Waves in a string, water, sound, alternating current, and heat for longitudinal. The mathematics for them, for now, is going to be the same. The amplitude is the maximum displacement. Amplitude right there, red line, and that is associated with the energy of the wave, which we're going to talk about not now, later. The wavelength, we usually use the Greek letter lambda, is the distance between the crest of the wave. The velocity, the speed that the wave goes through the medium. It's not the speed the medium is moving. It's not the speed of anything in the medium that's moving. The speed of the wave through the medium. The frequency is the number of cycles per unit time, and the period is the time it takes to complete one cycle. Traveling waves move at velocity in the direction of propagation. In this session, we're discussing one-dimensional propagation. The water waves in the first slide were two-dimensional, going horizontally and vertically. Sound waves are three-dimensional, because wherever you are in space, you can still hear sound. If a wave travels with a velocity v and a wavelength lambda and a period t, the formula x is velocity times time is lambda is velocity, the wavelength times the period. Can you rewrite this formula in terms of frequency? Let's do that. The frequency is the reciprocal of the period. If the period, which is a time, is in seconds, the units of frequency are reciprocal seconds. We call these units hertz. Since the period is wavelength over velocity, the frequency is velocity over wavelength. A wave along a stretched spring has a velocity of 12 meters per second. If the period is 0.085 seconds, what's the wavelength and the frequency? So let's figure that out. The wavelength lambda is going to be the velocity times the period which is going to be 12 meters per second times 0.085 seconds. Seconds cancel out, and our units are meters, and it's 1.0 meters. The frequency is 1 over the period, so that's going to be 1 over 0.085 seconds, and that's going to be 12 hertz. Okay, easy enough. Let's look at question 2. A boy throws a rock in a pond. The distance between the two ripples is 13 centimeters. Every 0.45 seconds another ripple appears. What is the wavelength? Now, that's a giveaway. If the distance between two ripples is 13 centimeters, the ripples on the waves of the pond are the crests. So we know the wavelength right away is 13 centimeters. The period is also a giveaway. If every 0.45 seconds that another ripple appears, that has to be the period. Oops. My pen slipped, sorry, I have terrible handwriting. Now, what about the frequency? The frequency is the reciprocal of the period for 5 seconds. And this is going to equal 2.2 hertz. Now the velocity is going to be the wavelength divided by the period (13 centimeters) over 0.45 seconds, which is going to be 29 centimeters per second. Now, I hope you learned something and that was useful to you. If you would like, please contact me and I can tutor you on the internet, just like this. Thank you.